journey in our office. Okay. So we have been working on adding dot detection in Gluster as upcoming release. I hope it's already done. 3.7. So it was, we designed it in a way so that it's extensible for the future. We wanted to have data compliance into which
just keep it out
here
of the so that it does not block the
bitrot detection, deduplication. So bitrot is one of the main consumers of the underlying compliance infrastructure. Okay, so what is data compliance? Okay, once you have lots of data, okay, you know, data compliance is generally an umbrella term that's used for things like detecting bad data, moving data around from cold storage to hot storage, hearing, and things like that. Yeah.
Can you stand over there? Can you stand over there?
Yes,
just from the camera point of view, just sorry.
Yeah. So things like deduplication and all those kind of things. Okay. So that's what the data compliance work is. Okay. So I'll just break up here and allow Johnny to talk about how we implemented bitrot detection. What does it bring? What all features it provides, and what's the underlying infrastructure.
Hi, my name is Raghavendra. So data compliance umbrella. So bitrot detection is the major things that will be coming for data detection. And
can you up your voice a bit?
okay. So under data compliance umbrella, so bitrot detection is one of the major things that is coming in 3.7 release. So what is bitrot like? It means like so because of some hardware failure, those kind of things, or backend UI is going bad. So the bits get clicked and your data goes wrong, and applications will be receiving wrong data instead of the data that they have. So here the purpose is like to detect such kind of backend going bad or hard drive failures, and identifying those files and those objects which are gone wrong, and so that application will be made aware or about those kind of bad data. So why is it needed? It's because as data gets older and older with age, there is more and more possibility of data going bad, and with Gluster since we use for many use cases, lots of data, there is a very good possibility that older data might go bad, and bitrot detection helps us to detect those kind of bad things, and so that and avoid application getting the bad data. So how bitrot detection is achieved is like, we could have done like one thing is like whenever a data is written to the disk, like we could have identified like the bitrot detection, like we sign the objects, like this is the signature of this particular object. So we could have done it synchronously during IOPA, but that is causing to affect performance very much. So because of that, we are planning to do signing of the objects asynchronously. It's like data gets written, then asynchronously the file is or object are signed, and even asynchronously they are being verified as well. Something goes wrong or like those kind of error detection, all those things are done asynchronously. And how are we achieving this error detection and signing of the objects is using object versioning. So we mainly use object versioning for achieving this, where each object, whenever there is a modification operation on that object, is signed with it is good, like whenever it's created, there will be a default version. Then whenever there is modification happening, the version keeps on changing. So we use that versions of those objects to identify and to sign the modified objects, and later even for verification as well we use the versions of that for each and every object for identifying the bad files and signing the normal modified files. So this object versioning like it's like, though bit rot detection is a consumer of it, it can be a generic thing. It can be used by other data compliance techniques such as even for clearing or maybe deduplication or compression. So even other things that fall under the umbrella of data compliance, they can also use object versioning for their own specific needs. So bit rot detection in this case is one such consumer of object versioning, and not just data compliance. We can even use for, like, we have something called upcall infrastructure that is being added in 3.7. We can use this object versioning along with upcall infrastructure to notify caching translator whenever an object gets modified, because its version has changed. We can send a notification to all the caching translators, especially like quick read or IO cache kind of translators, which cache the data which has been read. So they can be notified. So this object versioning is like, it's a generic infrastructure which we can use for other purposes as well. And not just that, like as part of bit rot detection, there were some like changes or infrastructure changes that were introduced, which as of now is bit rot detection is the only consumer. Later it can be consumed by others. For example, timer wheel. So we have our own in-house timer, but the timer wheel that has been introduced as part of this change is more granular and it has been well tested as well. It was like imported from the NS kernel, so it's well tested. And apart from that, we have token bucket based filtering for throttling purposes, so that the signing or verification, those jobs which are done asynchronously, do not consume more resources or do not end up consuming a lot of resources, so that IOs should not be affected at any case. So we can even use those throttling and timer wheel infrastructures even in our regular IO paths as well. In our normal in process we can use, so that and especially for service provider daemons like selfie daemon or rebalance, for requests coming from those, we can use them to throttle those daemons and they don't end up affecting any of the normal regular applications IO. So we can, so though it's like the object versioning or timer wheel or even the throttling mechanism we introduced, bit rot detection is the first consumer of it, but it can be used for even other anyone who needs throttling or timer. Those can use generic purposes as well. So this is about object versioning and bit rot detection. So about the other data compliance methods such as peering, probably.
So talking a bit more about object versioning. Okay. Yeah. So how this can be useful, and let me go into a bit more detail of how things work. Okay. So the main idea of object version is to track objects, when they are written to, and any kind of daemons like the bit rot, which is implemented as a daemon itself, or things like deduplication daemon, or things which may arise in the future. So the thing is, whenever an object is opened or written, you assign a version to it, okay, an initial version, and then on further modifications, you kind of come from the versions, okay. And so bit rot detection as of now, works in a way that it signs object when all the file descriptors are closed. A release gets triggered, and then you sign the file and attach the signature to that particular object. Okay, so how this is helpful there is, once you have written an object say multiple times, maybe a VM image or whatever, the version gets incremented, and at the time you close that particular object, okay, which means you are done with an object, you notify these services, just like say, for example, bit rot daemons, to to do the job and attach that particular signature to that particular version. Okay, so you start with version 1, do a bunch of writes, okay, close, and then you have version 2. So your file is now signed with version 2. Okay, and if you open it again, so the thing is, the client applications which are doing these IOs and the Bitrot daemon and the verification daemon, which is the file system scrubber, don't really interact with each other. Okay, so it's kind of, they don't talk to each other. They kind of figure it out using this object version whether the signature is stale or not. Okay, so if the version of the object at the time of investigation of that object and the one it is signed with are same, you probably have a version which should a signature which should match the exact signature of the object, which means it hasn't been modified. Okay, so this is a kind of there are set and get interfaces to the object versions currently used by Bitrot. We feel that this would be helpful for things like deduplication, compression, encryption, on disk compression. You might want to compress an object using the same policy, which is like when all the file descriptors are released, and when you compress it, you can assign, you can tag that particular compressed object to the version, and when you read it back, you kind of compare it again whether my object has changed. If not, you just read back compressed object. This is what we have with 3.7. Okay, going into other data compliance mechanisms like tiering, which is again for 3.7. We feel that our infrastructure here is extensible enough to support data tiering. Currently, it uses the SQLite-based interface. What we feel is you can stack up multiple. Before that, the underlying infrastructure, a part of the infrastructure is the chain log library that's used to get notification from the file system. What we can do is this is extensible. You can actually place a LRU or a LFU translator about chain log or whatever, track the hotness and coldness of objects, okay, and stream that information back to things like tiering, which could inspect these counters and take a decision of whether to move data or not. Currently, that's being done using SQLite. It's working great, but we feel that if we have that, the thing is, once you place things in a translator stack, they are much more, they become available to all. Okay, the chain time recorder translator that's been developed for the tiering feature is again sits on the brick itself and is in the IO path. Okay, yeah. So there are multiple approaches to the problem. Currently, the tiering guys use SQLite. We feel this is another approach which might work out of the box. Okay. Yeah. Again, we develop this infrastructure keeping the future in mind. We may want to do deduplication, compression, encryption. Dan here would be talking about the deduplication library tomorrow. So we may need to see how to fit this infrastructure with that, and how to things collaborate and do this in an effective way. I already talked about compression and encryption. You can use the similar object versioning mechanism to compress objects on disk, or even encrypt objects on disk and read them back, and even know the staleness of the objects based on the versions. Okay. So, what does it bring to us for 4.0? Okay, we feel we have done the clouding work, developed the infrastructure, introduced algorithms which are we have not reinvented algorithms. We have pulled some of them from the Linux kernel itself. The timer wheel algorithm that's used to track objects for execution by the Bitrot daemon has been just pulled up from the Linux kernel. It's well tested. We chose that in favor of the existing Gluster FSS timer mechanism, which is a linear linked list. So that's in place. We feel that the token bucket algorithm for throttling, currently it's only used by the bit throttle daemon in the sense it's put as a part of the bit throttle translator stack. It's not even a translator, but it's kind of integrated with it. So we feel that we have done most of the plumbing work. Okay. But the thing is, there are other things to look into, like deduplication. Once we have, once we get to know how Dan, has been thinking about his deduplication work, maybe we want to see how we integrate it with our current implementation, and for 4.0 we should be able to get to a better stage of compliance. I don't have many slides, that's it. I put this up last night.
So developers.
Any questions? Yeah.
The SQL like thing is well, that's what we have at the moment. We're looking for, always looking for new ideas. And it was meant to be extensible. But I wonder if you're trying to, can you talk about how it scales? I think you have many thousands of files.
Yeah, so the thing is, so a normal timer implementation, say it's a linked list, it could be a sorted or an unsorted linked list. So say it's unsorted, your insertions are open, you just go to the end and patch it. Okay, removal is open, given that we use the existing list-based implementation, but expiring, that's what you get. You have to scan all the time. So given that you have a million objects to track with variable timer expiries, and say even the granularity is second, okay, not even milliseconds micro, you have to scan the entire list every second. Okay. That really doesn't scale with millions of timers. So what the timer-aware algorithm does is actually a variant of a memory hogging algorithm, which is like, you say you have your expiry is 32 bit, okay, you have a bucket for each bit, okay. That's the most ideal implementation, but it's memory hogging. You readily eat all the memory. So what the timer-aware does is splits this whole big list, okay, into a set of 5 lists, okay, and assigning each list a set of range values for the expiry. Okay, and how timers are inserted in the timer wheel is you sort the time, you lazy sort the time. So when you, so you have these 5 lists, okay, each of the lists get a range of timeouts. Okay, so when you're inserting an object for expiry for timeouts in T1, you kind of figure it out where in the 5 lists it sits, okay, and insert that object there, okay. So and the clever thing here is you don't insert the object with the timeout for the whole timeout value. You logically split the timeout in chunks. So what the kernel uses is a logical split of 8, 6, 6, 6. Okay. So the first 8 bits, it splits the timeout values into 8 bits, 6 bits, 6, 6, 6. Inserts using the last. So obviously, if your timeout value is big enough, it will sit in the last list. And and there's a running timer, okay, for each list, okay, that scans the list every 1 second. That's the granularity, okay. And once you have expired that many ticks, you kind of cascade your object from last to the subsequent one. Okay, so an object that has a bigger timeout value will sit in the last list and kind of hops over till it ends in the first list. And so what you're doing is lazy sorting the timers. So when you insert it, it's kind of sorted. Say it sits in the last list, it's kind of sorted. Then when you move it, it's more sorted. Okay, till it comes back, till it comes to the first list, it's now fully sorted. Is you can actually expire. Okay, so the complexity here is insertion is over, removal is open, and expiry is all of them. Okay, so we get best of both worlds. Okay, with the list-based implementation, even if you had a sorted list, okay, your addition takes a hit. Your addition is O(n), but your expiry is kind of O1. Here we have O1, O1, and O out of 10. Okay. It's used by the Linux kernel. There is a single timer wheel instance in the Linux kernel used by the ISL system, used by networking all the pieces. Okay, so it's proven.
Yeah, well, let's talk more about
Yeah, sure.
after the.
Yeah, sure.
So, where do you see, say, compliance attributes like one or read-only and auditing for that fitting into the picture here?
Well, as I understand now, all of these read-onlys and worms are basically just translators implemented and live on the
Yeah, but I mean,
translated stack.
for somebody to consume that, right, I think we would also need a nice auditing framework because that's what people typically look for. I mean, if there's a one violation, I mean, they will need to figure out from where that's happening. And I think the term compliance itself has much broader scope.
It's a pretty
Yeah.
generic. I mean, it fit
So
anything.
maybe, I mean, that's something which we can.
Yeah, even if you had worm and any kind of write directly to the bridge,
Yeah.
the Bitrot can catch it, but it really doesn't stop the the write lookup.
Right.
Yeah, it's kind of
Yeah.
because of its asynchronous nature, you have to live with this as of now, unless you have sharding and where you can do here you can sign chunks or objects in the IO path rather than doing it asynchronously. But yeah.
So one of the things that I didn't understand, well, with the bit rot detection, now I get the object versioning and how each version has like a signature attached to it, like a checksum or something like this, right? So let's say you've got like a large VM and the VM is like 40 gigabyte file. When a new reader comes along and the bit rot detection has written a signature for that file, when a new reader comes along to open that file, where does this bit rot detection happen? Does it block the reader from opening the file until it knows it's good, or is it a background process that just runs and sort of flags things when they're wrong? Or
So you have something called a signer, which is the one
Yep.
you're talking about, the process that actually attaches the
Yep.
signature. There's another thing called the scrubber, the file system scrubber.
Okay, yep.
That it's a periodic scan of the file
Okay, a
system.
background process that runs and does it.
It's
Okay,
scheduled. You can normally you would run scrubbing every bi-weekly or whatever.
Cool.
Several runs weekly.
Sure.
Okay, they're more efficient. So that's the guy who does the scan of the file system for each object, verifies the attached signature to the one calculated, and it goes through the same route. Okay.
What happens when something's wrong? So like,
So to figure out something's wrong, it should actually pass a series of tests.
Mhm.
So the first test being the version should match.
Yep.
Okay. Once it passes it, you're sure that there is no active
Yep.
IO going on.
Yep.
Where the calculated section and the on disk
Yep.
stored section should actually match.
Yep.
If it doesn't, you're sure that somebody has either written
Directly to the brick or
because
something.
if you go through the mount, you increment the version.
Yeah.
So that's the staleness part.
Yeah, in the time that something's broken, in the time that something is wrong, what then happens?
Yeah. So what happens is once you detect that there are mismatches, you actually flag that particular object as bad.
Okay, yeah.
Yeah. And what the IO path actually does, which is not currently in for 3.7, is check this particular attribute.
Okay.
Okay. And obviously, since most of the deployments would be a replicate or a
Yep,
distributed setup,
heal across,
you actually hop onto the other particular break, do the same series of tests there.
Yep.
Okay. And obviously, there's a less chance that you'll be encountering the same problem there.
Two bricks problem, yeah.
So if you end up in that situation, you're screwed. So,
Yeah.
so in an distributed setup, you should be able to,
It should
recover
be
the
able to fix
chunks,
it.
using the codes.
Yeah, you just delete one chunk and it should
Yeah.
automatically recover. Yeah. It would be very cool to make it automatic because I mean that. Yeah.
Exactly.
Yeah.
And
So when I think about data compliance, a big thing that occurs to me is that there's, in U.S. terms anyway, Sarbanes-Oxley and data compliance, and there's the European. Bit rot detection would be a critical piece for those. But what are we thinking about in terms of not just object versioning, but object expiring objects and making sure they get deleted?
Yep.
And make sure, or not deleted based on compliance type legal framework. What are we How do we think about those?
Frankly speaking, we haven't thought about those.
Yeah.
Okay, but it's, given that compliance is such a representative term.
Our sales engineers keep telling me that we have big opportunities if we can do this stuff.
So this is just a start.
Yeah, object expiration would be nice. I mean, so because the life cycle of the object tends to be much larger than that of all of us. So if somebody just sets a policy, say that this object will be deleted 100 years from now, so can we actually do that? So that would be really cool.
Gluster version 58, yeah.
Yeah.
Actually, the 100-year rate would be 25.
Those way,
Throttling is something else we need to think about it. It's not a part of the compliance way.
Right.
It's just a way to not overheat your CPUs. Because as of now, if you just run it full throttle, and you have a bunch of VM images, you max out the CPUs. You really don't want that to happen. So you have a bunch of algorithms in place, the token bucket thing, token bucket,
Yeah.
all this kind of things happening. So that's the infrastructure part.
It's all good.
Any questions or only?
Cool.
thanks.
Yeah.